civil servant, like in a way His Excellency Governor Narayanan, but of course I never reached those stratospheric heights. So I am here because Professor Sinha, I think, wants to show that the higher levels of physics can be accessible to ignorant laymen like myself. I'm now going to request Dr. Shushanto Dattagupta to speak. He has been Vice Chancellor Vishwa Bharati, Shantiniketan. He's been Vice President of the Tagore Center for Natural Sciences and Philosophy, and is a Senior Scientist of the Indian National Science Academy, affiliated to this Bose Institute in Kolkata. He has published 7 books and edited 5 compilations on physics. He describes his research interests as non-equilibrium statistical mechanics, dissipative quantum systems, nanomaterials, fluctuation spectroscopy, quantum optics, and quantum solids. Professor Dattagupta, may I request you to try to compress your speech within 30 minutes, please? Thank you.
Well, when a foreign secretary ordains you doing that, how can I say no? Before I begin, Mr. Chairman, I would like to explain to all your audience here why I'm here and what my understanding of what this conference is all about. On the latter question first, this is not just a conference on the technical aspects of QCD, quantum plasma, cosmology, accelerator, physics, etc. But it's also a gathering of friends and admirers of Vikas Sinha from all over the world to celebrate his 75th birthday, an event which unfortunately had to be postponed by nearly 2 years because of the pandemic. I consider myself a close friend and an honest admirer of Vikas Sinha, but I'm really not competent to speak on the intricacies of Sinha's myriad research work over decades, for which he is internationally known. I'll only tangentially connect to his work via my own forays in physics, which are in the areas of condensed matter and statistical physics, as Mr. Chairman said very kindly. But perhaps more importantly, I'd like to discuss here Vikas the person, his cultural dimensions, and his multitude contributions to the society. This explains the title of my talk, the first word being ideals, the dictionary meaning of which is vision. That leads to idea. However, if that idea remains locked in the realm of fancy, it is not useful. The idea has to be implemented, another I. And that has to be functionalized through institutions. It is Sinha's invaluable contribution to institution building that will occupy much of our attention in the next half hour. Before I do that, it's incumbent on me to explain why Sinha is a product of the East and indeed of the West, a symbiosis of 2 distinct cultures. After schooling and undergraduate study in Calcutta, Vikas went to Cambridge University, photo of that, in the UK for physics tripos and subsequently for a PhD degree in 1970 from London University. Following that, he carried out postdoctoral research at the King's College of London, see a photo of that, before returning to India. It is these 12 years of stint in England where he came into intimate contact with true luminaries of physics, most notably his teachers, Sir Neville Mott, and also his master of Christ College, Lord Todd, Alexander Todd. When here's Neville Mott, here is Alexander Todd. When Vikas imbibed the Western values, intellectual honesty and hard but relaxed, enjoyable work that characterized the Cambridge atmosphere, And it's not just the interaction with physicists, but also the society at large, be it in operas, theatres, concerts, the cricket fields of Cambridge that shaped his cultural refinement. That is not to downplay, however, because his very strong cultural moorings acquired from his family days spent in Paikpara. Now, to many of you, you have a pointer here? So we're in Salt Lake City. Wait. So we're in Salt Lake City, and Paikpara is about 15 kilometers, but the driving time may be 1.5 hours, and that is where his ancestral home was. And so, as I said, that his Paikpara is also at the heart of Calcutta, from where he went. Sorry, I would like to show you first. Let me show you his ancestral home, and this is the Paikpara Rajbari. And from this place, he went to Scottish Church College in Calcutta, and subsequently, this is where he went for his schooling and Presidency College. But where is Gandhi? This is again his abode, and here is a photo of the district of Murshidabad. Here is the district of Murshidabad bordering on Bangladesh, and this may not be so well known to our overseas friends, so this is what I'm showing you. And here is Gandhi. Mark this also a place, this is where Murshidabad is. As a sign of Sinha family's deep commitment to education, they established an emancipated school called, and this is his Gandhi home, and this is the Gandhi Raj High School in the year 1857. So my school friends probably should know that is also the year when India saw the first uprising, called the Sepoy uprising, against the British Raj. You can discern from these pictures that Bikash belongs to wealthy nobility of Bengal. Interestingly, if I may go back to the map of Murshidabad, and it's coincidental that yours truly also comes from Murshidabad. He was born in a place called Jiaganj, but albeit in a much more modest setting. For our Western friends, it may be pertinent to know that Murshidabad was the capital of Greater Bengal, the Nawab of which, Siraj-ud-Dullah, was defeated in a battle in 1757 by Lord Clive of the East India Company that germinated the British governance of India. When the weather is more congenial, I suggest to my overseas friends to visit Murshidabad for its fascinating historical sites. There is one other interesting coincidence, and that is the specific year of 1976 when Bikash and I both returned to India permanently. He from the UK and I from the USA, and both of us joined the Department of Atomic Energy. However, he and I came to two opposite corners of the Indian peninsula, the ARC in Bombay, and I was in the backwaters of Tamil Nadu in the so-called Material Science Laboratory of the Reactor Research Center, now called IGCAR, Indira Gandhi Center for Atomic Research. I adapted to the research center's emphasis by applying my acquired knowledge in response theory, diffusion, defects, phase transitions. I mention these topics because, as it turns out, all of them have overlap with Sinha's own contributions over the years in completely different areas of nuclear and high energy physics. I'd like to discuss them a bit now. In the mid-1970s, Vikas Sinha made an outstanding contribution, a novel application of what we in our parlor call the linear response theory and the Kubo formula. This is in the context of the optical potential and nuclear structure applicable to nuclear reactions of light charged particles as well as heavy ions with nuclei. He did an imaginative calculation by relating the nuclear response to the field of the projectile with the imaginary part of the optical potential. This is quite akin to the magnetic scattering cross-section in my own area being connected with the imaginary part of the magnetic susceptibility. The starting point is the well-known Fermi golden rule from time-dependent perturbation theory, which my student friends from Calcutta colleges are aware of. And that states that the probability, capital P, of transition per unit time from an initial state in which the projectile is in the momentum state Ki, and the system, in this case the nucleus, is in the energy state Vi, to a final state in which the corresponding quantities are Kf and Ef, is given by this formula. But the last entry is an energy-conserving Dirac delta function. The crucial quantity, however, in the above formula is this operator V, which is a scattering potential. Sinha made an innovative advance by incorporating in V an effective two-body potential taking account of the saturation property of strong nuclear coupling. This point has been amplified in a paper by Shashi Pathak, my new in Pittsburgh, and Vikas Sinha, a paper called Nuclear Response and the Imaginary Potential for Nucleus-Nucleus Collisions, Nuclear Physics A 1983. In this paper, the field created by one nucleus and the nucleons of other nucleus is evaluated by treating the other nucleus as a Fermi gas. This yields the imaginary component of the non-local nucleus-nucleus potential, in which the intermediate states correspond to the particle-hole excitations of the Fermi surface. A couple of invited review articles bear testimony to the efficacy and usefulness of this approach. Later, in a related piece of work, Sinha computed the mean free path, or the mean free time, of a nucleon for a nucleus-nucleus collision, similar to the computation in solid-state physics of the Drude collision time or relaxation time that determines the electrical conductivity. This is Vikas Sinha mean free path of a nucleon in nucleus-nucleus collisions, Visred letter 1983. These findings of Sinha have significant implications for hotspots formed in the nucleus-nucleus collisions. Now I come to discuss diffusion, dissipation, and quantum friction. After returning to India and in the early part of 1980s, Sinha transited from medium energy nuclear physics to high energy heavy ion nuclear physics, delving into questions on what happens deep inside the nucleons. That is the genesis of his interest in quad-gluon plasma, we call it QGP, in which the quarks are like Brownian particles. So think of a Brownian particle like a pollen particle in Robert Brown's experiments in 1820s, and it's in a sea of gluons. And so you can imagine, and this is a model that I'm using after Robert Swansea and Tony Leggett and Ford, that you think that this pollen particle or the quark is connected by harmonic springs to a bunch of gluons, a whole sea of gluons. A simplified this is analogy with Robert Brown's experiments, as I said, and Albert Einstein's analysis in 1905 is that quarks are like the Polar particles, as I mentioned, while gluons are similar to water molecules in Brown's experiment. This naive picture would of course have to be elevated to the level of quantum, this equation, in which the Brownian particles or quarks would have to be endowed with quantum mechanical attributes, whereas the surrounding heat bath would have to be envisaged as a many-body collection of bosons and fermions. This scenario is very much along the lines of topical interest in quantum Langevin equation. So based on the model depicted just now here, this is again for my college students, what you do is you start writing down a Lagrangian of the basic quantum particle, which is in this case the quark, let's say, and you couple them by springs, so you have harmonic coupling to a bunch of gluons, and so from the Lagrangian you start writing the equations of motions. You get equations of motion for the coordinate capital Q of the central Brownian particle in terms of its momentum P and the mass capital M. And then this is actually Newton's law. dP dt, rate of change of momentum, is force minus the negative derivative of the potential energy Q with dQ. And then you get an extra term because of the coupling, harmonic coupling with the other particles. And then you write the equations of motions for the other particles. Little qj's are the coordinates again for the C of gluons. Pj's are the momentum variable, m is the mass, and here is the momentum equation again. Now you see, here you pause. You started out with a Lagrangian or a Hamiltonian, which has unitary evolution, but you want to get dissipation out of it. You want to get a viscosity out of it. So you can only get it when there is no time reversal invariance. But these basic equations have built-in time reversal symmetry. So what you do is, you do three things. You integrate the equations in the forward direction of time. So already you have a bias. You've given assignment of the arrow of time. Then you integrate out the other degrees of freedom, which you call the heat bath degrees of freedom, namely the gluons. And the third thing you do is that you assume that your heat bath is at the thermal equilibrium at a fixed temperature, pressure, everything, determined by the Gibbsian statistical mechanics. The outcome is actually then an equation which is now the quantum Langevin equation, where the time reversal symmetry is already broken and you have a memory function here. So if you did not have the heat bath, then you won't have these two terms, but you only have the first term and the third term, the Newton's equations of motion. But this term is actually the masala, that is where all the masala is. I mean, this is a friction term, and here is the quantum noise operator. And so this is in fact what we call the quantum Langevin equation. It should be borne in mind that the coordinate Q is derivatives, dq dt, d2q dt squared. They're all quantum operators which do not commute with each other. A related semi-classical approach is due to Jani Alam, Shivaji Raha, who was there in the podium in the inaugural session, and Vikas Sinha, in a paper called Successive Equilibrium or Equilibration in QGP, a PRL in 1994, in which a Fokker-Planck equation is written down, which is given below here, where zeta is once again the friction coefficient. We ignore now the memory effects, because now you write zeta of t minus t prime in terms of a delta function in time, and Tf is the fluctuation dissipation relation of the diffusion constant that has the usual dependence of the temperature, and the subscript T on Nt implies that the latter depends on the thermal mass. Now it is well known in non-equilibrium statistical mechanics that from the Heisenberg picture of quantum Langevin equation, one can arrive at the Schrödinger picture density operator, which to the Wigner function representation can be reduced to this classical distribution function that Jane Alam Shivaji Raha and Vikas wrote down. And the cube, however, the quantum Najamani equation is a more general treatment capable of handling strong coupling with the path and arbitrary temperatures where quantum effects are dominant. I now turn to QCD phase transitions. A significant discovery of Vikas Sinha's research group in the 1980s was that the QGP is indeed a distinct phase of nuclear matter reached by means of a phase transition in the hadronic world. One important ingredient of this finding is that the ratio of dileptons to photons, as well as the ratio of pi mesons to dileptons, are snapshots or suitable signatures of this new phase. It is also established by Sinha's group that these ratios are independent of the baryonic potential at a critical temperature, thus rendering the signals for the QGP independent of the baryonic background. Later it was also discovered and discerned that the ratio pi 0 divided by gamma can be a true signal of the QGP, provided measurements are made within an appropriate kinematic window determined by simultaneously measuring the ratio of dilepton to photon. The theoretical claim of photons and dileptons as possible signals of QGP has been justifiably incorporated in the experimental nucleus-nucleus program at the CERN LHC, the Large Hadron Collider, as well as the Radioactive Heavy Ion Collider, acronym RHIC, at the Brookhaven National Laboratory. Now, my final technical issue is on phase diagrams, quark nuggets, etc. So now I fast forward and qualitatively discuss Sinha's recent theoretical interest as typified in Vikas Sinha, Hawking radiation from strange quark nuggets, relics of the QCD phase transition, PhysRev D 2020. Well, you already heard about Hawking radiation from Roger Penrose. But before that, here is an elementary discourse on phase diagrams for the student audience here. Shown is the phase diagram in the pressure temperature plane of the most common system on Earth, and that is water. So as you know, water, if you heat, you can go from the liquid phase to the gaseous phase. All of us know how to boil water. But if you cool water slowly, of course, then you get into a solid called ice, and then the liquid, solid, and the gaseous phase coexist at a point called the triple point. But this is the part which is interesting. This is where you go from the liquid phase to the gas phase, where if you cross the line, your thermodynamic densities change, like the entropy density, the specific volume, etc. So you have a first order phase transition. However,